So here we want to take a look at triple integrals in spherical coordinates. This is a typical spherical coordinate integral. So you can see in this we're integrating with respect to rho and then phi and then theta. Rho is going from 0 to 1, phi from 0 to pi over 2, and theta from 0 to 2 pi. So just like in the beginning, it doesn't matter to us what variables they are. To integrate first with respect to rho, we just imagine the sine phi as a constant. The integral of rho squared would be rho cubed over 3. So let's integrate that. Substitute the 1 and the 0 and subtract. Then we'd want to integrate with respect to phi. Well, the integral of sine phi would be negative cosine phi. Leave the 1/3 alone. Substitute. Then we want to integrate that with respect to theta. That would be a 1/3 theta. Substitute the 2 pi and the 0, and there's how we evaluate the integral. Now, we could also have used the properties that we discussed several times already. Since the limits on the integral are all constants, and the integrand is separate functions of phi, rho, and theta multiplied together, we could just split it into separate integrals. Integrate each one of those and multiply them together. Now, typing this into the TI-89, you can get the Greek letters by pushing the second and the CHAR, which is above the plus sign, and typing the Greek letters just like they're printed. Oftentimes, however, I'll just transpose letters. Maybe use an R for rho, a P for phi, and a T for theta. So here we want to set up the integral over the region bounded by the cone. We can type this in maple. In the hemisphere, that's the upper half of the sphere, and the two together would look like this. Now we'll take out all of the excess figure. So here's the region that we're trying to describe. So let's take the cone first and change it into spherical coordinates. So we're going to replace the x squared plus y squared with r squared, and then the square root of r squared is just an r. Now we replace the z with rho cosine phi and the r with rho sine phi, and then solve for phi. Now on the sphere, we'll square both sides, move the x squared and y squared over to the other side and change that to rho squared equals 4, and then rho would be just a 2. So our triple integral will have the factor rho squared sine phi, like we learned in an earlier section, is always in the triple integral when you set it up in spherical coordinates. Integrating with respect to rho first would be 0 to 2. Integrating with respect to phi would be 0 to pi over 6. And then, of course, the theta, to get us a complete revolution, would need to go 0 to 2 pi. And you notice this, we can integrate with the property that we've used several times before, 3 separate integrals, and the integral of each one put together. Now we'll convert this triple integral in rectangular coordinates to spherical coordinates. And just like in cylindrical coordinates, we want to split this into 2 components. First, take care of changing the region, then take care of the integrand. So 2 conversions. Now I have a Maple document that you can enter the integral and it will show you the region. That's called visualizing region. And here is what I typed already. This is what I've got from the Maple document that shows me what the region here looks like, and I want to convert that. Again, we have the factor rho squared sine phi that we have anytime we change to spherical coordinates. Now the theta is just in quadrant 1, which would be 0 to pi over 2. And the rho, let's see how we can find rho. Now rho is the distance from the origin out to the surface. Now we need to figure out what that is. Now the surface, if we look at this, we're going from 0 up to z, and we're told here what the z's are. And obviously this would be the one we're going to. So using z equals square root of 18 minus x squared minus y squared, and the fact that x and y are both zeros, we get z equals square root of 18, which we can simplify to 3 square root of 2. And so our z's then are going from 0 to 3 square root of 2. So now let's see how we can come up with the phi. Now remember, phi is the angle from the positive z-axis around to the edge there. So we need to describe that. Now, we will take the red surface. This is the red surface, and do a little changing. The x squared plus y squared is r squared. And if we move the r squared to the other side, we get z squared plus r squared equals 18. So that's a description for that red surface. Now we will take the blue surface, which is described as z equals square root of x squared plus y squared. And again, we will replace the x squared plus y squared with r squared, and we just get z equals r. So we can find then the intersection of those, the seam between those, by combining these 2 equations. So we'll take the r equals z, and we'll replace this r with z. Now that'll give us z squared plus z squared equals 18, 2z squared equals 18, or z squared equals 9, So z would be a 3. And so this seam right here corresponds to z equals 3. Now for z equals 3, we will take the conversion formula, z equals rho cosine phi. We will use the 3 for z and the 3 root 2, which we found earlier, for rho, and we'll solve for the phi. And so we find out that the phi for this is pi over 4. So there's our limits on the phi. So putting those into the integral, we would have the rho going from 0 to 3 root 2. We'd have the theta going from 0 to pi over 2, first quadrant. And then we'd have phi going from 0 to pi over 4. The only thing left is for us to convert the integrand. X squared plus y squared plus z squared converts into rho squared. And so there is our integral in spherical coordinates for this one. The thing about converting is oftentimes in situations like this, we end up with an integral here that has just constant limits, which is much easier to evaluate.